The broadcast is now starting. All attendees are in listen-only mode.
Hello everyone, and thank you for attending today's webcast titled Simplify Your Simulation Workflow with Autodesk Nastran In-CAD, presented by Forrest Judd, Solutions Engineer with Hagerman & Company. We also have Mark Lautenbach, Solutions Engineer for Hagerman, on the line to assist with your questions. This presentation is being broadcasted in a listen-only mode. You can ask questions by typing them into the question section of the GoToWebinar control panel, and Mark will address those questions throughout the presentation. At the end of the broadcast, when you exit GoToWebinar, you'll be prompted to fill out a short 3-question survey. We ask that you take a few moments to provide us with your feedback. Also, all attendees will receive a certificate of attendance and a link to the recording of this presentation. Forrest, whenever you're ready.
All right, thanks, Brianna. Good morning, everyone, and thanks for attending the webcast this morning. Our topic today is Autodesk Nastran In-CAD and how it can simplify your simulation workflow. So, as Brianna said, we're going to have questions. You can have questions during the presentation. Please type them into the question panel. Mark will be addressing those as we go. I'll be keeping an eye on them as well. So if something particularly pertinent comes up, I may address them as well. And there'll be time for a Q&A at the end. So our agenda for today, I'm going to start with a brief comparison of Autodesk simulation products. The portfolio is getting rather broad, but that's mostly because there are a lot of different simulation needs. So we'll talk a bit about the various products and where each product fits in the simulation world. Then we'll go through an overview of Nastran In-CAD's features, and I want to show you several different analyses. My plan is to spend a lot of time in the software so you can get a good look at it, and try not to PowerPoint you to death. So Nastran In-CAD, if you've not heard of it before, is a general purpose FEA tool. And it lives inside your CAD system. That could be both Autodesk Inventor or SolidWorks. It works the same in both pieces of software. And there's some real benefits, of course, to having your CAD program inside, or your analysis program inside your CAD program. The fact that you don't have to go out to some other piece of software, you don't have to worry about translation. You can work in a familiar environment is great. And the fact that it's still powered by the Nastran solver gives you a lot of capability, right? Much more capability than, say, what's built into Inventor Professional right now. So these are as far as the mechanical simulation products go, these are our three, well, I guess technically four main products. We have Inventor Professional, right? Which some of you may have used. In fact, I've got a poll question I'm going to ask you here in just a second. We have Autodesk Nastran In-CAD, which is maybe a step up from that. Then we have Simulation Mechanical, which is another step up, and then Autodesk Nastran, which is a full-featured solver you can use with lots of different pre- and post-processors. And really, each of the products has a pretty well-defined role given your simulation needs. So I'd like to start with a poll question here. And I'd like to know if you currently use Inventor Professional's simulation environment. If you use it, if you don't use it, and maybe why. All right, thank you very much for voting. We have a lot of responses coming in, and it looks like over half of you think you could use Inventor Professional's environment, but you don't know how to use it. And it looks like a few of you say you use it and there are things it doesn't do for you, and some of you don't use it because it doesn't meet your needs at all. Right? So we can just take a look at the results right there. So it looks like most people here have a need for simulation one way or the other, and either Inventor Professional is meeting their needs or partially meeting their needs. So let's take a look now at kind of how Inventor Pro versus Nastran In-CAD versus Simulation Mechanical, where they fit in your workflow. So Inventor Pro, it's only for linear static stress with linear material models. So if you're like big chunky parts or very simple thin parts, we recently added the ability to do plate elements. Very limited basic contact. Things that are already touching metals, not plastics, slowly applied loading, fixed parts, welded joints, really basic stuff. And it's great, that does meet a lot of needs, but that doesn't meet every need. That's why we might need something like Nastran In-CAD or Simulation Mechanical. So when we get into more complex frames, like very large frames, maybe with pinned joints, the fact that you can stay in Inventor is great. We can do, say, dynamic loads, impact loading. We can do vibration analyses. We have complete nonlinear capabilities in In-CAD so that we can do things like plastic parts and composite materials and rubber and elastomers. And we have more advanced contact types, right? So parts can start out not touching, and then at some point in the analysis they can come into contact. You can't really do that with the basic Inventor Pro, right? So the nonlinearity ability, both in material types and simulation types, the advanced vibration, those are real key benefits of using something like Nastran In-CAD. Simulation Mechanical, there's a fair amount of overlap between Nastran In-CAD and Simulation Mechanical. The real differences there start to become when you get into large assemblies with a lot of different material types, when you get into advanced motion, a lot of kinematic, a lot of just motion where parts are moving, long distance as opposed to, large deformations. A lot of it really has to do with the UI and the way that you assign materials and the way that you assign, element properties. So, Nastran In-CAD is really a fantastic fit for a really broad range of analyses. Linear static, of course, buckling analysis, both linear buckling where you get kind of a load factor, or also, straightforward, like more traditional nonlinear buckling. Normal modes, right? If you're going to do vibration, that's a key, first step. Heat transfer, that's a big one that an Inventor Pro doesn't do at all. Composite materials, advanced contact types, transient analyses, which Inventor Pro just can't do. The advanced material types, impact testing, which we're going to see an example of that as well. So let's get into the analysis types that I want to discuss today. The most common one I think of that most people might use would be, a linear or a nonlinear static analysis. We can do the linear static in Inventor Pro, but if you get into advanced contact types, or if you get into large deformations, a linear analysis just isn't going to be effective. It's going to, not give you appropriate information. So for the linear, you're limited with static loads, slowly applied loads. The nonlinear capability, though, gives you the ability to create a more realistic simulation, right? More advanced contact types. Nonlinear materials, large deformations, right? Those are, depending on the materials you work with or the operating conditions of your equipment, it may be very important to introduce the ability to solve nonlinear problems. So let's take a look at how you would approach a problem like that in Nastran In-CAD. So you see I'm an inventor here. Nastran is just another environment, right? So much like you might go into your stress analysis environment, we can go into the Nastran environment. It's just on a ribbon. We've got some familiar tools up here, and the UI is well laid out to kind of walk you through how you might go through an analysis. You can also interact with the model tree over here. So much like I might start another analysis, I might start out with materials. Now the materials we can assign either from our CAD program, right? So Inventor's got a pretty good library of materials. Nastran comes with a very large library of materials as well. Right. So I know in this case what I'm looking for, we're going to simulate this plate and how it might rest against this stop as we apply a load on the far end here, and it'll be pinned at the back. So we're expecting a fairly large deformation here, and this is where we might want to investigate linear versus nonlinear. So I'll start with the linear approach. And we have an aluminum material here. We're going to have a steel material as well. Let's go with a nice one of these. And now I'll just assign those materials to the components, right? So this plate is aluminum. And our stop here is steel. And we can name these as well. So this is our stop. One thing I like about Nastran is we sort of have this model area of the tree, and then we have our actual analysis. And I can create materials and physical properties, meaning an assignment of element type and material to geometry, and I can choose whether or not those get used in the model. So if I have several different subcases or analysis types, I can quickly reuse these, be it constraints or element definitions. I can quickly reuse those as opposed to having to redefine them over and over again. That's one thing that I really like about In-CAD. In terms of meshing, this is an assembly, so we can choose to mesh all of the parts with a similar mesh size, or we can dictate a mesh size for each component. So I'm going to mesh them independently here. So an element size. This is another thing I really like about In-CAD versus Inventor Pro. Is Inventor Pro, your mesh control is very limited. There are definitely times where I'd like to say I want this mesh size. And obviously with small features, it's going to increase the mesh density as you get the small features. But in general, I want this exact mesh size. You can't really do that in Inventor Pro. You're sort of limited to a percentage of the bounding box of the material. So I've got some materials applied. We'll go ahead and update our mesh. So the mesh is very straightforward. It's a great mesher. It happens really fast. And now we're ready to apply some loads. Now we're going to do the static analysis here first. And that's where you might often do if you're not sure if maybe large deformations are coming into play and impacting your results. You might start out with a static analysis and then move on to to a nonlinear. So I've got some materials applied. I'm going to do some constraints now, and I think we'll fix the back of the plate here. We will fix the bottom of the plate here. Our constraint dialog, this is laid out very well so that you've got the ability to assign symmetry and the ability to control very easily your specific degrees of freedom that are constrained or unconstrained. You can do that in Inventor Pro, but it's not at all obvious how you do that. It's kind of tricky. And there are no nice, easy symmetry buttons. Of course, we always want to take advantage of symmetry if we can when we're doing an analysis. So this is fixed, this is fixed. We're going to apply a load here at the other end of the plate of 200 pounds in the minus Y, 200, not 100. And now we need to deal with the contact. Now we can specify contact just in general and say, you figure out what contact is. But we can also explicitly define a contact pair, both the contact pair and the contact type, be it general contact, which is we're not sure they may or may not be in contact to start with. They may or may not come into contact during the analysis. It may be sliding, it may be, not sliding, we're not sure. So we can go with general and then it will figure out as we go. But we can also, apply things like welded, for if we know the pieces are fixed together, or offset weld, which is really nice if you've got gaps. If you're trying to actually, analyze a weldment that you've left room for weld material or whatnot, you can do that very easily here. We're going to stay with general in this case because it may separate, probably not with the way we've loaded it, but we want to make sure it can both slide and separate if need be. And that's something we just fundamentally can't do with Inventor Pro. All right, so we've got a mesh, we've got some constraints, we've got a load, we've got our material properties, so I believe we're ready to solve. Now this does run in the Nastran solver, right? So the same solver that's been used for years in the aerospace industry and a lot of other industries. And you get a lot of feedback about the analysis here. You can always hide this output. This is giving you an idea of what it's doing. Right? You can always switch back to your model tree, and if you really want to get under the hood and take a look at the actual file that was sent to the Nastran solver, you could do that here as well. I believe we're almost done. It takes a little bit longer with this advanced contact type. And now we can take a look at our results. So post-processing is pretty good. We can look at contours on our model. We can look at deformation, of course. We can animate all that. The typical, results review, you might have lots of different result sets that we can look at. So we're not like in Inventor Pro, we're limited to, principal stresses and von Mises stress, deformation, and a safety factor. We have a lot of different result sets here. We'll take a look at, this is aluminum, on the plate here, so we'll look at solid von Mises. And, there we go. We can see our maximum stress here is about 14 kips, which is, I think it's acceptable in this case. What we really want to look at is our deformation, because we're concerned whether or not, nonlinear effects are going to come into play here. And I mean, 14 inches of displacement. I would definitely want to run this, nonlinear just to try it out. Right. So we can do that. We can just switch the analysis type. But in this case, too, we had to apply a specific type of constraint here at the back so that the problem would solve, because linear problems expect your parts aren't going to move. they're going to deform a little bit, but they're not going to move in any significant way. So I'm going to apply a more realistic constraint because this pin, maybe this plate is actually pinned, right? So maybe we can rotate about this edge, but we're not allowed to translate. And then I'll switch my analysis type. It's very straightforward. Switch analysis types to nonlinear static. And of course, with a new analysis type, we've got some more information to assign our nonlinear setup here in this case. And this is where we can determine whether we want to see our intermediate steps or not, or if we want to go right to the end. And also the number of increments we're going to solve. Increments in this case, because the way nonlinear solution like this works is it slowly steps up the load, and then at each increment, if necessary, it will recalculate the stiffness matrix. And that's going to give us more accurate feedback as to, specifically what's going on. Now, just like that, we're running a nonlinear analysis. This is going to take a little bit longer. Notice it because it's iterating for each increment, so it'll be up to 10 increments. The number of iterations is going to depend on how long it takes the model to converge at each increment. Notice because we're looking at our intermediate outputs, we can actually get a look at in this case, the solid von Mises as the analysis is proceeding. Now this is fairly fast. We're almost halfway through. I think I'll just let it run out here. It'll be done shortly. And what we're really looking for is, are there significant differences, say, in stress or in deformation especially? Especially if we're concerned about deformation of this plate. We want it to deform, sure, but there's a limit to the deformation that we can accept or that we're looking for. And again, anytime you've got large deformations in a model, you really do need to consider whether or not nonlinear effects are coming into play. And a basic linear static stress analysis will not do that. Almost done here on our last increment. And we're done. So let's take a look at our displacements. Now, because we've got our intermediate outputs, we can look at the situation at any of these load cases. We're interested in the actual deformation. We see actually our maximum deformation here is 16 inches. So that's 2 inches of additional deformation over what the linear case told us. Right, so in this case, it did make a difference, right? Our linear case, we had, 14 and 3/8 deflection, and in our nonlinear case here on the left, we've got an extra 2 inches of deformation. If nonlinear effects were not contributing to it, there might be a small difference, but it wouldn't be that significant. I mean, we're talking, more than 10%, right? Where if nonlinear effects were coming to play, I mean, it might be 1 or 2% at the most. So in this case, maybe doing a nonlinear analysis is going to get us a lot closer to what our real-world situation is going to be. So beyond just being able to capture nonlinear effects, both in because of deformation or contact or material type, we can do a whole host of other analysis types within CAD that can add a lot of value to your digital validation. A big one is dynamic response, right? The ability to include time and mass and investigate how things respond to vibration or external drivers. Seem like random excitation or time-dependent loads, time-dependent motions. So if a load starts and stops, what impact is that going to have? frequency response. You've got a conveyor with a drive motor operating at a certain frequency. You want to make sure that it's not going to shake itself apart, right? And we can do some of that, like a little bit of that in Inventor Pro, but we can only do a modal analysis. So we can get an idea of, you know, what frequencies we might want to avoid if we're talking about vibration, but we don't have any way of quantifying what actually is going to happen to a part if we get close to that natural frequency, and just how sensitive is it to external drivers, you know, that are cyclic. So let's take a look at a couple different analyses. Or we'll start with a simple modal analysis, and I'll go ahead and at least constrain this like it should be. So this is aluminum. I've already sort of set up some of this, so I won't have to go through it again. So this is, I had other analyses in this file. So I've already specified that this is, you know, solid elements. It's made out of aluminum. Can change our mesh density here. And we might constrain, say, just fix the bottom face here. And that's all we really need for a modal analysis. Got a material type, we've got a mesh, we do have one constraint, so we could run this. Oh, let's get an update here. Let's see. Let's take a step back here. Make this out of aluminum. Actually, I think we're having an issue with the one of the other analyses here. Let's just get rid of these. Interesting. Let's clean some of this up. I wanted to have some of this done before so we wouldn't have to wait for an analysis, but I thought maybe I should clean it up here. All right. Get some of these things. All right, so our model is meshed. I'm going to start with a clean file here. Sorry about that. There we go. So we're going to make this out of aluminum. There we go. So this is just the modal analysis, right? So I asked it for 10 different modes. And so we can see here, the first few modes are, of course, I didn't have any constraints, so these are just the rigid body modes. And then we can see like these first 6 really that are very small. So it looks like our first, our first mode here is about 658 hertz, and then we calculated a few more, right? Let's run again with that base fixed, see what we get. There we go. So our base is fixed. Ultimately, it's down, going to be bolted or welded to a table. And so with the fixed base, it looks like our first natural frequency is about 209 hertz, which we can do that with Inventor Pro, but we don't necessarily know how sensitive it is to loading at different frequencies. And that's where we might want to do, for example, a direct frequency response. So what this lets us do is actually define a load at a particular frequency. So I could say, for example, that we know that something is on this bracket and it's shaking. And so it's in the minus y direction. But notice now that my particular analysis type is direct frequency response. I can actually apply a load factor based on frequency. And in this case, the load is going to be the same, right? So I do need to provide something. But we know we're going to, because our first natural frequency was right around 210 or so, we're just going to say the load is the same regardless of frequency, but it is, cyclic. So while the load is there and it's constant regardless of frequency, we do need to indicate what frequencies we're interested in, investigating. So it's going to be across a range of frequencies because we want to maybe hit a couple or see, as we approach a natural frequency, what the response is going to be. So our lowest, we're going to start at 100 and go to 300. It's going to put our first mode like kind of right there in the middle. And we're gonna basically from 100 to 300 hertz, we're going to go 25 increments there, so in 8 hertz increments. And of course, we're going to add a little bit of damping here. I think we'll go with structural damping in this case, so just 5%. I believe we're ready to run now. So this is basically, running for across each of the frequencies that we specified the load might act at. And so we do have quite a few results here. There's some default plots. We can always make our own plots as well based on any of the result sets. But there's a good one here already, maximum displacement versus frequency. And we can see right there at that first mode that we were expecting, right about 212 in this case, we see a huge peak in terms of displacement. We actually see, a pretty ridiculous amount of displacement. So we can see just how sensitive this is. And then we might, go back through and tighten up and say we'll go from 200 to 250, and just run again and see what we get. Because the analysis takes very little time to do, so we can really investigate just how sensitive is this to excitation around the natural frequency, its first mode there. And we can see it actually, it's pretty bad. We want to stay pretty far away from that first mode, or we're going to see some pretty undesirable behavior. Right? So if we were to go to, say, 210, which is about the worst, which is right in line with what we were talking about, right? Our first mode was at 210. We could take a look at the displacement, and we can see obviously something bad would happen before it really got to that point, I think. But if it somehow maintained its structural integrity, it would be a bad thing to hit that natural frequency. All right, so on to heat transfer. Now, Nastran, we can do, I would say, simple heat transfer problems, steady state or transient. We can do conduction, radiation, and convection. And the nice thing is you can transfer those temperature results to a structural analysis as a thermal load. So if you need to be, if you're concerned about thermal stresses or deformation due to temperature differentials, you can use Nastran to develop a thermal solution that you can then port those results to a structural analysis. So we're going to take a look at a pretty simple example. Just have a heat sink here. And we've actually have, this is only a quarter of it, right? So we're taking advantage of symmetry in this case. And we've got a heat flux coming in from the bottom. This might be sitting on a chip or something. We've got some air blowing across the fins. And so ideally what we want to do is we want to see, given that convective load and the heat flux, we want to see how long does this thing take to reach a steady state temperature, and what is that steady state temperature. So that's the problem we're going to try to solve with this model. So I'm going to check my units here. Our units for our Nastran analyses are just, you set those by the document analysis, document units, just like you would everything else in Inventor. Let's see, I think we'll make this out of aluminum. In fact, I'm going to start with a clean file again here, just to avoid any issues. Looking for aluminum. In this case, we definitely want to make sure that our thermal properties are correct, right? Because we're going to be looking for our specific heat and our coefficient of thermal, like our thermal conductivity. So we definitely need that kind of information. We also want to make sure and change our analysis type. Lots of different analysis types here. Right now we're looking at transient heat transfer. And let's go ahead and take a look at our mesh. This is a pretty small part also working in millimeters, so we're going to say 2 millimeter mesh size. In fact, we can go with linear elements here too because it's a thermal analysis. Make things a little faster here. Right, so our loads, heat flux is one of our available loads. In this case, you do need to apply heat flux, so you have to know, say, what your total, say, wattage, for example. You do have to calculate that based on the surface area. So it looks like a pretty high value, but it's just because it's a pretty small small heat sink. And this is transient, right? So we need to indicate, you know, how our load might change with time. Now in this case, it's the heat flux, we're just going to say it's constant. It doesn't vary, right? So at 0 seconds, right? So 1, and we can just go to 1 second. This is what we call like a unit table, which just means it's constant throughout the analysis. Our heat flux is applied to that surface. All right, so we've got our heat flux. Now our convection. Right, and our convection is going to be on all of these, all the fins, but not the back wall of anything. That's symmetry, right? So down in here, we're going to avoid the whole. These two are external, but these two faces are symmetric faces, so we don't need those. We do want the inside faces of the fins here. Our ambient temperature is going to be 298 K. And our convection coefficient. So this is something that you have to know. Generally, you know, in a case like this, you might be able to like look it up in a table or estimate it. If you've got more complex geometry, you can always use something like SimCFD to do a flow analysis that would let you determine your convection coefficients. And we'll say our convection is constant as well. All right, so we have convection, we have our heat load. So now we're really interested in, you know, determining how long this is going to run, right? So this is a thermal analysis. We can use pretty big time steps. We know this is going to take a while to reach steady state. So we'll go with each time step is going to be 500 seconds, and we'll let it run for 10 steps, right? So the total analysis time is going to be 5,000 seconds. And we'll leave our step method as constant here. One last thing we forgot was our initial temperature on everything. Initial temperature, 298. And then off we go. Right, so this is going to run through just a transient heat transfer. It's going to step up the temperature. So these are all our time steps here. And it's pretty, it's pretty fast. So we can maybe take a look at a plot, pick any particular node here on the surface, and we're looking at temperature, I believe. Let's just take a look here. Oh, I think I forgot to do one other thing. Yes. my result set, it would help if I said I was interested in temperature. So let's run it one more time. That's better. All right, we just look at a plot here, our maximum temperature versus time, and we can see, obviously it's going to ultimately, tail off here. So it looks like our steady state temperature is around 465, and we do reach our steady state roughly by the time of the unit analysis. So we could always add a few more steps if we were interested in what happens, but this gives us an idea of how our heat sink is going to perform, and then if we do have issues, thermal stress, we could always take this temperature data and use that in an analysis for like a thermal stress analysis, for example. All right, one last analysis type I'd like to cover is impact analysis. I get a lot of questions about how you might do this in Inventor Pro. And the answer is you really can't, right? Because Inventor only does linear static stress, and so the idea there is that your loads are applied evenly and slowly, and any impact is anything but slow, right? But the fact that we can do nonlinear analyses in Nastran means we can do impact analyses, and there actually is a tool in Nastran to help us set up these impact analyses so that we can actually get them up and running very fast. Because these things, depending on your geometry, can take a long time to run. They can be tricky to set up. So it's nice that we have the ability to set these things up quickly. Let's take a look. It's going to be, pretty straightforward, so it solves quickly. We just have a ball that's going to ultimately drop onto a plate. Notice this plate is actually a surface model. We can analyze mixed element types in Nastran very easily, right? So that can help you optimize your model. In this case, we don't need all of that solid geometry. We're just interested in what happens when the ball hits. So as usual, I'll start with my physical properties set up. I know I want the ball to be made out of steel. And we'll make the bracket out of aluminum. And again, we can mesh each component with its own mesh size if we'd like. So we'll make the mesh a little bit bigger in the interest of time. And of course I need to set the thickness on that flange. All right, so we'll say it's an 1/8. There we go. And I want to reverse the normal on this too. Because I believe we're probably pointing the wrong direction. So let's see here. Yeah, everything's kind of pointing toward the inside. Oh, let's see, I missed a couple of faces as well. There we go. There we go. So now we're going to get proper contact saying this ball is going to hit this side of the plate. Now we're going to fix the back face here. And now we're just going to set up our impact analysis. So this is our projectile body, right? The ball is what's actually going to be falling. And then we can pick our path here. So ultimately the ball is going to be falling in this direction. And our acceleration, this is just gravity. Right? So it's just falling due to gravity. Save it. I believe now we're ready to solve. So this is all automatically determining the optimum, time step, and ultimately a lot of the tricky things that you might have to otherwise specify, like how long does the ball take to get down to the bracket, and how what should my time step be to accurately capture everything that's going on. It sort of just figured all that out for us. Now you notice down here the stress is, we can see the shelve on Mises here, the stress on this guy changing. The ball hasn't moved. That's because while it's solving, it doesn't actually show the motion of the ball. But it ultimately is doing that. And when the analysis gets done, we'll be able to take a look at that. I mean, we're almost done here, the last time step. Oh, maybe we got a few more. So I think what we'll do in the interest of time, because we're almost out of time here, I'd like to take a look at this that I already have. Oh, actually, I think we overwrote that. So we're going to let this go. I think it should be done soon. But ultimately what we're going to see is the ball will have bounced, several times on this plate. So while that's running, let's just talk a little bit about some of the other analysis types. Simple linear buckling we can do, Euler buckling, and also nonlinear buckling. It can account for large deformations, for contact, nonlinear material types. Buckling is one of those things that it can definitely be unpredictable. There are certain structures that lend themselves to buckling, so maybe a linear buckling analysis might help, but otherwise, to really know for sure, you're going to have to do a nonlinear buckling analysis, and we can do that in CAD. We can handle composite materials, both 2D and 3D laminated elements. For example, you can build up a composite with plies, their thickness, their material properties, and their orientation. And of course, we can do fatigue analysis, vibration fatigue, response spectrum, a whole host of different analysis types that ultimately can, help you prove out your products digitally before you go on to build them. All right. I believe we're almost done with this now. Ultimately, what we're going to see is this thing just is bounced here. So this is the sort of like what we're seeing is it ultimately does bounce. So while this is still going, do we have any questions? Oh, I think it's done. So we'll go ahead as we take a look at this. We'll open it up for questions as well. We actually haven't gotten many questions so far, so feel free to ask questions now. No questions so far. A question for Mitch. What are the hardware requirements for this software? It really kind of depends on the analysis types you're running. My laptop here, I have 24 gigs of RAM, a mobile Core i7. An SSD is really nice for large result sets. Honestly, if you can run Inventor pretty well, then you can run Nastran. Just may depend on solution type, solution time, really. Good question. Can you generate mid-plane shell model in Inventor? Inventor Pro has a fine, thin bodies that it can do. If you want to do shell models in Nastran, you have to draw the surface models yourself. That may be easy or difficult depending on what your model is like. If I'm creating something that I know I'm going to want to run a shell analysis on in Nastran, I'll start with that from the get-go. I'll create a shell, use that to optimize my design, and then from there I'll look at solidifying it into manufacturing geometry. And that workflow works really well, especially early on in a design iteration. Any other questions? Can this software be done as a network license versus standalone? All Nastran is sold only as network license. It works with both Inventor and SolidWorks. The same license can work with either piece of software, and it's always network in this case. And in fact, most Autodesk software has an additional fee to activate it for network use. Nastran right now at least doesn't. It's the same price, and they're all network. If you do want to run it kind of as standalone, like in my case, it's on my laptop, you can put the license manager on your computer and just use it just like if it was just installed on your laptop. Yeah, and so Mitch asks, if you have 5 engineers, can you have one license and then they can check it out? That is correct. So you could have it installed on several different systems. Only one person at a time can use it. But ultimately, I think that's the reason it's network licensed anyway, is because that's really the most cases. I mean, most people aren't really doing analysis all day, every day if they're going to use a tool like Nastran In-CAD. So they, when you need it, it can be there for you, and you can have one license or 2 licenses for a group of 4 or 5 people. It is one of those tools that once you have it, you might think you don't need it very often, but once you have it, you tend to use it over and over. Can you input nonlinear material property like plastic stress strain curve? Yes. Yes. You can apply all of those materials, and there are different material theories you can use. All right. Well, I think we'll call it there. We've reached the top of the hour. So I guess if you want to keep asking questions for a minute, we'll be here. But otherwise, that's the end of the presentation. I thank you very much for your time this morning.